The first average or amortized running time analysis I would like to do is about the constant increments resizing strategy. My assumption is you have already studied and familiarized yourself with the code over here, especially about when the maximum capacity is reached. How exactly do you do the resizing by growing the array of the size of the array by some fixed constant, right? That's something to assume. Let's now try to do the analysis over here, right? So what we're doing here is we're doing the so-called amortized analysis or average case analysis. The idea is pretty simple. What we're going to do is think about how you calculate the average. We're going to calculate the total amount of running time divided by the number of operations, basically, right? So that'll be the total running time, which we're going to calculate first, and then divide that by the number of operations, right? It's a very simple formula you know about how calculating average, right? That's what we're going to do. And exactly how do we calculate the total running time? We need to just go back to the code and I'll visualize exactly what's really happening about resizing. And I will use these arrays over here to really show you the different phases or different occurrences of the resizing. We'll get to the diagram in just a moment, and eventually we want to know what's really the amortized or average running time for the first resizing strategy using constant increments, right? That's kind of the roadmap for this part of the lecture. And we're making the following assumption. Since we want to analyze about the push operation itself, right? Just remember the worst case time. I want to emphasize again, it's so important. So this part over here, we know that this part over here is actually worst case big O of n. The worst case. Okay? The worst case is big O of n because we actually got the resizing part over here, right? Let me just highlight it over here. You can see this part over here. By creating the new array and also by copying all the contents from the old array into the new array, right? So for this part, the logic is pretty straightforward. I don't need to trace the code together with you, but that one there is definitely big O of n in the worst case, right? But what we want to know, what we want to analyze is over here. We know the insight over here. This does not happen always. You don't really have to resize the array every time you call the push operation. That's really the insight, right? Does not. How about this? This only happens once in a while. I'm trying to be a little bit vague over here, but what do you exactly mean once in a while? That's something I will visualize for you. Okay, this only occurs once in a while, not always. In a while. Right, so these are the two insights which I mentioned in the previous part. I would like to repeat them very quickly, right? And of course, this part over here is really done unconditionally every time. And this part here is just about the push itself. And that's really the part you're also familiar with, right? This part here is constant, right? We can simply ignore that just for now, right? Because constant is not going to dominate the running time. And for this part over here, we know that it's simply just big O of 1. And we are simply just going to disregard them from our analysis because we know that eventually we just have to drop them. But of course, if I want you to consider the entire method for the analysis, of course you want to include them as well. But for that one, I'll let you do the exercise. I want to focus purely on how we can analyze the running time for this part over here, right? And this part over here, we know that it's actually big O of n. That's what we know. Worst case, right? Let's now talk about the resizing. Let's now try to visualize the different occurrences for the resizing. Okay, and we also make some assumption over here. So without the loss of generality, we assume we got n pushes, right? So we want to count the pushes for n times. That means eventually we want to have a stack of size n items. Well, of course, right? If you push the stack for n times without running into any exception, in that case, you should really have a resulting stack with n items. That's obvious, right? And the last push is going to trigger the last resizing routine. So meaning that after pushing n items into the stack, we're simply just going to execute this block of code over here for the final time, meaning that we are still going to copy all the existing n items of the stack into the new array. And how big the new array is depends on which strategy we're using. If we're using fixed constant, we'll see how exactly it goes, and we'll see how exactly it will go accordingly for the doubling strategy, right? Hopefully the context is clear to you. Let's now use this diagram over here to really try to help us formulate our series of the running time for the individual resizing. Let's now try to look at how the resizing will be proceeded as we go for the n pushes. Initially, we're going to create an array of size I. As you can see from the code, initially I will be certain constant over here, and then we simply create the array. You can see capacity is assigned to be I, and then array size will be capacity, which is I, right? So that means I'm going to use the green to really indicate all the slots are now free to be stored some elements. So I'm going to say all the I slots in the array will just be free. That's the initial array. No resizing is done, right? We are just executing the constructor over here. And what about the first resizing? The first resizing is going to occur if all the initial I slots have been filled out by the items. In that case, we actually have to copy over all the I elements into the new stack, the new array. And more precisely, we're going to create a new array of size, the current capacity, which is I, plus the fixed constant C, meaning that we're going to get this particular array, first of all, created. And then we're going to copy over all the filled out slots, which will be I. Otherwise, we wouldn't need a resizing. In that case, we're going to copy them over to the I. Right, let me try to use a different color here. So that means for the first I slots over here for the new array, they will be still occupied. They're simply copy over from the old array over here, right? And then after this, we can also make the final C slots actually available for any new pushes, right? That's really the first resizing. If you understand about the first resizing, all the subsequent resizing until the end will be following a similar pattern. And how much work does it really take for this resizing over here, right? Creating this strictly bigger array, which is over here, is actually pretty cheap. That one is actually just a big of 1. It's mainly about this loop over here, which is to copy over all the I elements into the new array over here. That's really the main computation we want to do. And that one will be exactly I iterations, right? To really copy over all the I elements. So I'll just put I over here. That'll be the work that will dominate the running time for this particular resizing. Let's now talk about the second resizing, which will follow similar idea. So the second resizing is going to be executed if we got this Boolean condition being true. What was the last capacity that we set? From the first resizing, we set the capacity to be I plus C, right? You can see I plus C. That's what we did earlier. In that case, we're going to do the second resizing if the I plus C elements from the first resizing have been filled out. In that case, what we're going to do, two things. Number one, we're going to create a strictly larger array, which is going to be I plus C over here plus C. And so that means this part over here will be the newly available slots for us to do further pushes. And then this part over here need to be copied over from the old array, right? So that means this part over here is going to be the loop that we're going to do, right? And also this part over here will be the newly available slots for us to do further pushes. And what's the required work for us to really complete the second resizing? Well, we're going to run a loop with exactly I plus C iterations over here, right? So we're going to say I plus C. I plus C over here. Let's do one more, and then we will be able to observe the pattern and go all the way until the end, right? What about the third resizing? The third resizing is going to be invoked if all the slots that have been made available in the second resizing, which will be I plus C plus C. Once we reach that particular size, we need to create an even bigger array, which will be I plus C, right? And plus another C. That's a fixed constant. So that means we have to make this array, and then we're going to copy over all the old contents over here. You can see the old contents over here correspond to exactly the size from the previous old array after the previous resizing step. In that case, it's going to create another C free slots for us to do further pushes. And what will be the work that's required to do this copy over here? I plus C, right? Hopefully, so far it's very clear to you about how the fixed constant strategy, fixed increments actually work. 2 times C over here, right? Let's now talk about what's going to happen in the last resizing, right? Let's now go back to our assumption. We're going to do n pushes over here, meaning that we're going to get exactly n items after the n pushes, right? And also, the last push triggers exactly the last resizing routine. So what we want to make sure is basically like this. For the last resizing, we want to copy exactly the n items that we have pushed already to the stack. So this part over here, I'm going to write is going to be simply just n. This part over here, right? And since we assume that it's going to trigger the last resizing routine, so that means after the resizing, after we have copied over all the n elements into the new array, and also we're gonna do the resizing, meaning that we're gonna make another C slots available for further pushes, right? So that's exactly what I meant by this particular assumption over here, right? So we need to have some bound in order to do some analysis. Alrighty, so far hopefully it's very clear to you, right? And we want to actually talk about exactly how to add up the running time from all the resizing over here. From the first resizing, second resizing, all the way to the last resizing. What would be the amount of work to be done in the last resizing? And for the last resizing, in this case, is simply just going to be n over here, right? Because we got exactly n items resulted from the n pushes. And that one there triggers the last resizing, which will increment the array size by just C over here, right? So what we want to do is to add up all these running times together, and then eventually divide them by the n pushes. So that will be the average calculation, right? Let's now do that, right? Hopefully you're following so far. I think understanding this diagram over here, how it corresponds to the assumption, is so crucial. We'll adopt some consistent consideration for the doubling strategy as well later, right? Let's now try to add up the operation running time, right? So the first resizing is simply just I, right? Plus the second resizing is I plus C, and plus the third resizing is I plus 2 times C, right? You can see these numbers over here as I explained before, plus all the way to the last resizing is going to take n, right? So far so good. And this is apparently an arithmetic sequence because we have some common, not factors, so we have some common increments over here, right? You can see we start with the initial term, and to really get to each next term, we have to plus certain increments over here, right? That's a very definition for arithmetic sequence over here. Right, so let's see how we can add this up together, right? Let me just make a little bit more annotation over here. This is the amount of work for the first resizing. Let me just put first over here, right? So this is the amount of work required by the second resizing, right? And this will be the amount of work by the third resizing, okay? Because in order for me to really apply the formula for arithmetic sequence, if you just try to remember, if I got some arithmetic sequence, let me just remind you very quickly. Arithmetic sequence. Let's say I got some initial term plus, let's see here, just make it even easier. If I got turn 1 plus turn number 2 plus all the way to turn, let's say k. Let's say if I got k turns, for example, right? In that case, I'm going to do the first turn plus the final turn multiplied by the number of turns, which will be k in this case, divided by 2. So that's the formula I assume you know already about the arithmetic sequence, which we spoke about also earlier when we did the asymptotic analysis. Right? So this will be very important for you to actually recall. Of course, this will be the sum of arithmetic sequence over here. Right? It's a very quick recall. And in order for us to, we know the first term, we know the final term, but we need to know how many terms are there over here, right? So that's something for us to figure out. So that's why we have to see the pattern over here for each term. In the case of the first resizing over here, let me rewrite it a little bit to help you. All right. So you can see the I over here, it will be equivalent to I plus 0 times C. All right. So this part over here is the first resizing. Oh, let me do a bit better. The second resizing is I plus 1 times C over here, right? You can see we got 0, we got 1, we got 2, all the way to over here, right? And let me just also try to do this one over here, right? For the first resizing, the factor over here is actually 0. For the second resizing, the factor over here is actually 1. For the third resizing, the factor over here is actually 2. You can see the factor will be exactly 1 minus the kth term, right? It's really important for you to actually observe the pattern for each term over here. So I'm just trying to show you as quickly as possible, just to show. But you definitely want to think about it yourself on a blank piece of paper. Okay, and let's say we got k resizing. Let's say here. So if you actually try to do over here, let's say this will be the kth resizing. So this will be the kth resizing, right? And we want to know exactly what k is. According to our formula, if this is the kth resizing, it should be exactly equal to I plus k minus 1 times C. Do you agree? This will be very important for you to make sure you understand before you move on. Actually, this is really the key to really make things work. When we later actually try to analyze the doubling strategy, we want to use something very similar. All right. Okay, what exactly is k over here, right? If n is exactly equal to this, we will be able to solve k. Let's now solve k together, right? So what I will do is I'm going to, let's say, can I just say this is actually star over here, right? I'm going to put a solve the star over here. So we say that I plus k minus 1 times the constant increment c is equal to n. So what exactly is k? K is equal to, I'm pretty sure you can calculate that, n minus I, right? N minus I divided by the multiplicative constant c and then plus 1, right? Right? You can definitely double check about this result over here, right? I'll let you check it. If you got any question about how to solve this, you can definitely reach out to me. But I thought that that's rather basic over here. So now we are done. Well, not done, but we are almost done. We know how many turns there are. This is the number of turns over here. You can think about this part over here. Why are we doing this? So this part over here is about the number of resizing. Number of resizing steps that we have to do. Each resizing step is actually going to execute this block of code, which will be big O of n, right? And so we got this many resizing to do, and we got the first term, we got the final term, so now we can add them up together. So what I will do is I'm going to apply the formula of the arithmetic sequence over here. A1 is simply just I, the first term, plus the final term is n, multiplied by n minus I divided by c over here, and plus 1, right? And then divided by 2, right? Again, you can see first term, final term, and also the number of turns over here as we calculated, right? So that's exactly what we have. And what would be the number? Of course, I can tell you the final answer directly. You just need to move around the terms and also do some simplification. That should be rather basic arithmetic you can do. Let me tell you the answer directly, okay? And you can definitely double check and tell me if that's actually correct. So it's going to be n squared plus c times n plus c times I minus I squared over here, right? So that's parentheses, by the way, over here, and divided by 2c. So this is as far as I could simplify over here, right? So this will be the final answer over here. This is basically the total amount of work. You can think about this one here correspond to the total running time over here. And we can, what would be the what would that be asymptotically, right? You can see the n squared over here dominates the running time over here, right? You can see n squared over here really dominates, right? So it's going to be big O of n squared. So this is a total running time. Total running time. And in order to calculate the average running time, we have to divide this by the number of push operations. How many do we have? We got n pushes, as we assume. Right? So now we can now calculate the amortized or average running time, which will be, right? So now we can fill out the answer over here. Amortized or average running time is going to be the big O of total amount of running time, n squared, as we just calculated, and we got n pushes, which will be big O of n, right? So this conclusion here, even though it's really, well, let me tell you what the conclusion is. The conclusion is, let me just try to just highlight the final result over here. So this is the final result that you have to know. That's why I put it in a small little sticker over here, right? So the conclusion is the worst case running time for the push, as we said in the beginning, is big O of n. Even after we try to do some rigorous analysis over here, and then we still find out, even average out the running time for certain number of resizing steps over n pushes, even that, we still get big O of n, which is okay, but at least we know the big O of n is a very tight asymptotic upper bound, either average-wise or worst case-wise. That's what we learned, all right? It's really important for you to understand both, right? Worst case is big O of n, and also the, let me just box a little bit better. So the worst case is big O of n, and also the average case is also big O of n over here. And we're going to adopt the same analysis for the doubling strategy and try to see if we just get the same average running time. Do we get the same? Do we get lower, or do we get higher? That's really the question. All right, let's move on to the next part of the analysis.